monitoring. I think you already met maybe a few of the people from the program at the Budapest event. So today you will present some work on applying fiber optic sensing and how it can be integrated into digital twin technology. So thank you again for being here. Sorry again, I would have to leave during the presentation, so I will not be able to join the Q&A session, but Ruben here will handle the session. So thank you all again, and Barnabas, you can start your talk. Thank you.
Welcome everybody. My name is Barnabas Szőke from AdvaNet Hungary, and in this presentation I will talk about the passive optical sensors and its applications and its role in digital twin technology. And at the end of the presentation, I will show you two use cases about the monitoring system what we installed. So digital twin is a virtual representation of a real system processor objects, and it's made by collecting real-time data from sensors, devices, and from any other sources. And after with this collected data and with mathematical models, virtual model can be created. And with this virtual model processes, or so we can use it for simulations, analyzations, optimizations, and also we can use for simulate future scenarios to predict failures. And as I said, the reliable and accurate real-time data is an essential part of digital twin. So optical monitoring system also can be an important part of it. As we know today, optical fiber is not only used for transmit or receive high-speed data. It can be used for measure several physical phenomena such as temperature, acceleration, stress, displacement, and any other physical quantities that can convert it into strain or temperature with a transducer that has a linear characteristic. There is lots of benefits of the optical sensors. The main benefits are the lifetime, that it can last more than 20 years, and there is no need to change sensors or calibrate them by time. The passive sensing, that means that it does not require power supply at the sensor site, and it can cover long distances that can be more than 50 kilometers, but it depends on the attenuation and the number of sensors. And high sensitivity and accuracy. So we can measure strain plus minus 1 microepsilon accuracy. The microepsilon is micrometer per meter, and we can measure temperature 0.1 Celsius accuracy. It can be applicable at a harsh environment. So it's not it's spark proof, so we can apply it at gas and oil sector, and it has immunity to the electromagnetic radiation, so we can use it areas where the electromagnetic radiation is high, such as high voltage substations and the transmission lines. There are several applications of the optical monitoring system. The main applications are the structural health monitoring. So we can we can use permanent and temporary monitoring of existing bridges, tunnels, and dams, and we can use it for measure the structural displacement of buildings or any other structures, and we can monitor the static or dynamic behavior of any structures. We can use it at the transportation, so we can use it for monitoring of road, pavement, vehicular traffic, and track-based traffic. And it can also provide several or wide range of data for smart city projects. There are security solutions in the telecommunication sector, such as there are lots of detectors, door opening detectors, cabinet door opening detectors, intrusion detection, and manhole opening detectors. And we can use it in energy sector because it's spark proof, and in the energy sector, for example, gas pipes, measure displacement of gas pipes, and the leak detection. There are two types of the passive optical sensors. The first is the quasi-distributed sensing. In this case, the measurement points are fixed and predefined. And there can be discrete sensors and also sensor chains. And the sensors can be connected in series or cascaded with each other. And there is a need of an interrogator unit. The interrogator consists of two parts: an optical part that provides the measurement signals for the sensors, and it also collects the back reflected signals from the sensors. And it consists of an industrial PC, so it can acquire the data and it can make the data processing, and also it can send the data via wireless or wired medium to servers or databases. The other technique is the distributed sensing. In this case, the measurement is along the entire length of the fiber, and it is based on the scattering phenomena. And it also requires interrogation unit, but in this case, the conversion from the signal to strain or temperature data is much more complex, and it requires more computing resources. So yeah, this also represents the quasi-distributed and the distributed sensing. Yeah, and in the quasi-distributed case, we can cascade the sensors, as I said, and we can place the sensors in multiple channels. And the interrogator unit can be requested maximum 16 channels. And in both scenarios, we can cover about more than 50 kilometers. There are some fiber aggregating based sensors like temperature sensor, strain sensor, acceleration sensor, weldable strain sensor, surface temperature sensor, deformation sensor, embedded into tilt, concrete and tilt sensor. And now I would like to talk about the working principle of the fiber aggregating sensors. It is a microstructure inside the fiber core, and this microstructure is a periodic grating. And this grating is modulated the refractive index of the fiber core. And if we attach a wide spectrum of light in one end of the cable, a very narrow spectrum will be reflected back to the input. And this is called fiber, it's called the Bragg wavelength that identifies the sensor. And this Bragg wavelength is the function of the period, the length of the period. We can produce the FBG with several techniques. One is if we interfere to UV lasers, we can make this microstructure, or we can also make a phase mask and after radiate the fiber with a high intensity UV laser. This shows the working principle, as I said before. So the Bragg wavelength reflected back. And how can we measure strain or temperature with this sensor? As I said, the periodic length change will affect the Bragg wavelength. So if we apply a force on the fiber or if we heat the fiber, so the thermal expansion can change this periodic length, and this causes a shift in the wavelength. And this wavelength shift has a linear relationship with the strain or the temperature. And we can cascade in the sensors. The only one exception is that the sensors in series should have different Bragg wavelengths, and during the operation, the Bragg wavelength shouldn't be overlapped with each other. The working principle of the distributed sensing is based on the three scattering phenomena. The first is the Rayleigh scattering, which is a elastic light scattering caused by the density variation frozen into the fiberglass during the manufacturing process, and when the light interacting with these molecular imperfections, it causes reflection uniform in all direction, and this amplitude of reflection is sensitive to acoustic vibration, strain, and temperature. The other one is the Brillouin scattering. It's a nonlinear phenomenon, and it's caused by the light is interacting with the phonons of the medium, and this causes a frequency shift in the backscatter light. It's called Raman. So it causes a frequency shift, and there is a higher and a lower energy backscatter light, and it's called Stokes and anti-Stokes. And it is sensitive to strain and temperature variation. It's called distributed temperature and strain sensing. And the other one is the Raman scattering. In this case, the light is interacting with the molecular vibration of the fiber, and this also causes frequency shift, and this is sensitive only for temperature variation, and it is based on the distributed temperature sensing. This is the schematic design of the optical monitoring system. So we have an interrogator unit and the UPS, and the sensors and the interrogator is connected with the fibers, and there are also more channels, but there can be more channels. And now I would like to show you some applications. The first one is the distributed acoustic sensing. It can be used for monitoring track-based traffic, or to detect several phenomena that can affect the traffic, such as a broken rail. In this case, the broken rail generates acoustic sound, acoustic pulse, and if the train passes through above it, we can determine the location of the broken rail. And also we can detect it that several phenomena alongside the track, such as working next to the rail, train passages, and laying down sleepers, railway sleepers. We can monitor the dams also, and with the distributed temperature sensing, we can measure the temperature distribution of a dam in function of the height. And this waterfall diagram shows that. The y-axis is the is the time, and the x-axis is the height of the dam, and the various colors represent the temperature. And from this data also we can calculate the average temperature of the dam. And we can also use it for gas and telecommunication and energy sector. Because it's spark-proof, we can use it for leak detection. We can use it for measure the displacement of gas pipes, and also we can use it for dynamic line rating and for measure the temperature distribution of transformers. Such as with FBG, we can also measure the temperature of every wirings of the transformer, and also we can measure the temperature of the oil of the transformer. In the gas pipe, in the case of the gas pipe, if we place distributed sensors, strain and temperature sensors in all the 4 directions, we can measure the flex or the movement of the pipe in all the directions. And if we place a sensor also next to the pipe in the ground, we can measure the ground movement. And with the distributed temperature measurement, we can detect leaks, and we can estimate the location. We can monitor the monuments, and we can detect or we can measure damages before it happens. What are the benefits of the fiber optic monitoring system against the classical electrical sensors? So it do not need power supply at sensor site, and it can cover up to 50 kilometers and 100 sensors per catalog. If we can expand the system easily, because we can connect in series sensors, and in the conventional case, the sensors have a complex cabling and difficult multiplexing techniques, so it's difficult to expand the system. And also electrical sensors has relatively low lifetime and resistance and high maintenance. So now I would like to show you a case study about a bridge monitoring system which we installed in between 2019 and 2020. A new bridge has been built on Erdalsó stations connecting tracks about the Velencei Road, and at my request we installed online permanent monitoring system with a quasi-distributed sensors. This bridge has been built with a new construction design, and is aimed to reduce the structural height of the bridge. And because of this new construction design, MAV requests for online permanent monitoring system, and the chosen solution was the chosen solution was the innovative fiber optic monitoring system and data collector system. So fiber optic grating sensors offer to monitor the bending of the bridge during the train free periods, and also during the train passages. And the configuration is engineered, and the design sensors were attached to the bridge from below. And we use for this project 4-channel interrogator unit, and it's placed in a nearby building at the Erd station, and there was power supply there. And this building is about a few hundred meters away from the bridge, and the customer is able to see real-time data from the bridge as the interrogator is available. And we integrated the data to the MAV's existing monitoring system. What was the project was? It's non-stop monitoring of the bridge and validation of the new bridge construction. And we managed continuous strain and temperature measurement across the three main cross sections. And we used also only fiber optic sensors and fiber optic cablings. And the data sending to the central monitoring server is also non-stop. What was the requirements from the MAV? That during the train-free period, we should send one measurement data from each sensors hourly, and we should detect the train passages. So one train passage is an event which we should measure with a higher frequency. It was 50 Hz. And in case of event, the data should contain 5 seconds before the event and 120 seconds, 50 seconds after the event. The event sensing is, as I said, was 50 Hz sampling frequency, and the measured data should be integrated to the existing central monitoring server. And the measured frequency or sampling period or sampling frequency should be changed easily by software. The bridge design is shown in this slide. The bridge has two ribbed main steel beams reinforced with concrete, and the railway superstructure consists of concrete track slabs, which are placed closely next to each other. And the steel concrete structure and the track slab jointly work together. The structural height of the bridge is 1.13 meters. In order to find out where to place the sensors, the designers carried out simulation to find out where are the critical cross sections where the highest strains can occur, and we put or place the sensors in these three cross sections, in the lower and the higher belts, in the lower and the upper belts, and we used strain and temperature sensors and long strain sensors, and we mounted the sensors into the steel and into the concrete track slabs. And also we had the ambient temperature sensor. This is the architecture of the monitoring system. So we used a 4-channel interrogator, and we used 3 channel of it. And at the middle, we placed the sensors at the joint of the track slabs. And we used weldable strain and temperature sensors, and temperature sensor and long strain sensor. In the case of the weldable strain sensor, the temperature sensor is embedded, and it is used for the temperature compensation of the sensor. So it's a block diagram of the software integration. So the sensors and the interrogator is connected with the fiber optic. And in the middle, it's shown the data process what the interrogator made. And after the data processing, the temperature and strain data is sent to the MAV's database and servers via VPN connection. There are some pictures about the installation. At the left side upper corner, you can see the cable in between the interrogator and the sensors. And we deployed the ducts and protection boxes for the sensors because the MAV asked for protection against vandalism. So we used IP68 protection boxes. And during the installation, the side of the car roads has to be closed. And at the last picture, you can see the finished installation. Yes, there are some other pictures, and at the last picture, you can see the interrogator. It placed at the rack mount with the UPS. And after the installation, we managed a load test with the MAV, with the Sergei locomotive, and it provided us static and dynamic loading. At the case of the static loading, the train stands on the bridge in 3 ways. At the first one, it stands at the left side of the bridge, and after the right side of the bridge, and after at the middle of the bridge. And in the case of the dynamic loading, the train passes through the bridge in both directions and with a different speed. This is the ambient temperature. This is the data of the ambient temperature sensor during the load test, and this is the load test combined measurement results. In the way of two-way pressing, you can see the signal of one strain sensor when the train passes through the bridge in both directions. And in the signal, we can estimate that the axle load of this train is asymmetrical. And if we analyze three continuous strain sensor signals in line, we can also estimate the direction of the train passage. This is a Stadler-Fürth train passage measurement signal from one sensor. The train has 5 axles, which we can see in the signal. And now I would like to show you a video about the load test. So at the bottom of you can see the signal of the train sensors. This is the first view. So now I would like to show you another case study, which is a asphalt pavement and the road monitoring system. It was a proof of concept. The test installation under real conditions, and the aim was to evaluate the feasibility of the fiber optic based sensor for real-time monitoring of pavement, and to get a deeper understanding of the impact of the environmental variables and traffic. And the location was between Acsa and Erdőkút, and this is a lower class 2-lane road. the goals of the test is to find out the installation process of the sensors, and we should integrate it to the pavement construction phases, and it does not cause delays in the scheduling. And we should also investigate the sensor design, because it should have enough protection and sensitivity. The protection, because of the construction vehicles can damage or so it can damage the sensor, and it should have enough sensitivity, because the sensors are placed in between the base layer and the first asphalt layer. And the design is designed to allow seasonal and comparative measurements. So the measurement system has two main tasks, as I said before. The sensor placed between the base layer and the asphalt layer under the expected wheel tracks, and also we should measure the pavement temperature profile vertically with temperature sensors. Which was the primary challenges of the installation. The paving temperature, it was 180 Celsius. The fiber optic operating temperature is below 80 Celsius in long term, but in short term the fiber can withstand much more temperature. So it doesn't cause any damage on the fiber. And the chemical effect, the emulsion, it should also not damage the fiber. And the construction vehicle passages, especially the track-based vehicles. And yeah, we use sensor changes. Two types of sensor chains. The first is the GFRP beast cable. It is a fiber reinforced polymer-based sensor cable, and optical fiber is embedded directly into the fiber press rod. And the other type was the filmed-based, what stands for fiber in metal tube. It is a metal tube integrated cable consisting of stainless steel reinforcements. Typically with polymer outer sheet. And we place the sensors in this design. So the film-based sensor we placed at the right side, and the GFRP-based sensor we placed at the left side. And we also use the film light traffic monitoring sensor to measure the speed of the vehicles. And we terminated the exit of the cables in a terminal manhole, and we made it redundant, so we can see the sensors in both directions. So if somewhere there is a fiber cut, if we use both the direction, we can see all the sensors. So this is the temperature sensor chain. There were about 30 sensors in series, spacing with 1 centimeter, and we installed it to the asphalt by drilling. This is the beam light sensor, and some pictures about the installation. So the first step was to clean the road, and after we fixed the sensors with I would say this so we fix the sensors to the road, and after it get the emulsion layer, and after the finisher laid down the first asphalt layer, and yes. we cut it to a dim light sensor in the first asphalt layer, and after the second asphalt layer lay down. This is the termination hole where the cables are exited, and we can connect it with the interrogator. Yeah, this is the asphalt temperature profile in function of the depth of the asphalt. And there are several measurements about trucks. In this case, there is a free axial group truck with the 4 sensor signals. Yeah, in this case, the 4 sensor signal. Yeah, this is the longitudinal direction, and the other one is the cross direction. So because the sensor placed in vertically and longitudinal. This is the GFRP sensors measurements at several passages, and the down or the bottom you can see one passage cross direction, but you can see the signals were not so intensive there. So thank you for the attention.
Okay, thank you very much, Barnabas, so for your presentation. If it's up to you, I will let to the audience if there is any question. I can read it from the chat if you want, or you can activate your microphone.